Dear students, let's continue to focus on haloalkanes and haloarenes, mainly on the concepts required to solve challenging questions in competitive examinations like NEET, JEE, mains, etc. Alright? Now, the topic of discussion in this session is absolute configuration. Alright, now before I get into the details of this concept of this particular topic, let me first make you clear about what is meant by configuration. Now, configuration means arrangement of groups, okay, arrangement of groups in space. Now, you may have come across this terminology while learning about isomerism, which also will be dealt with in detail later, okay. So, under isomers, you have learnt about two main classification, two main topics, types, namely structural isomerism, stereoisomerism, right? Now, stereoisomerism is what involves the arrangement of groups in space, all right? And stereoisomers are further classified into geometrical isomers and optical isomers. So, in class 11, you have learnt that geometrical isomers can be classified further into cis and trans, right? So, cis and trans are configurations. Cis is a specific arrangement of groups in space. Trans is another specific arrangement of groups in space. So, the specific arrangement of groups in space is what is known as configuration. So, geometrical and optical isomers are configurational isomers. Alright. So, geometrical isomers, you have learnt it last year in class 11. There is one more type of geometrical isomer, apart from cis and trans, you also have E and Z, which will be tackled later. Alright, not in this particular session, but in a session exclusively devoted to isomerism, stereoisomerism. Similarly, under optical isomerism, you have already come across while dealing with the introductory discussions on haloalkanes and haloarenes, especially when we discussed SN reactions. There we came across the fact that optical isomers exhibit optical activity, right? That is, they can rotate the plane of plane polarized light to the right or to the left. So, you had dextro and levorotatory forms. But dextro and levorotatory forms are not configurations. They are just depicting the direction of rotation of the plane of plane polarized light. So, here we are going to focus on how to determine the arrangement of groups in space around a chiral carbon. So, chiral carbon is what is in focus when we talk about optical isomers. So, in this model that has been created, you notice that the central atom represented by the black color is bonded to 4 different colors. So, 4 different colors imply 4 different groups, and hence we call the central atom as the chiral atom, and this atom happens to be carbon. So, chiral carbon or asymmetric carbon. And this has been discussed in detail. This is only for a recollection. Alright. Now, the importance of chiral carbon is that it is a structural requirement for exhibiting optical isomerism. So, what is optical isomerism? Optical isomers are non-superimposable mirror images of one another. Alright, so I have created the non-superimposable mirror image of the first form. So, you notice that these are 2 mirror images which are non-superimposable. Okay, I am not giving more examples. It has been dealt with in detail earlier under SN reactions and optical isomerism. Okay, now here, how did we distinguish between these two isomers, stereoisomers or optical isomers? We distinguish them on the basis of the difference in optical activity. So, what was optical activity? Direction of ability to rotate the plane of plane polarized light in a polarimeter. Again, I am not going into the details. Alright. So, one of the 2 isomers, if I place this isomer in the polarimeter, this may rotate the plane of plane polarized light to the right, and therefore we would call it as the dextrorotatory form isomer, and this will therefore rotate the plane of plane polarized light to the left by equal amount. So, angle of rotation is the same, but the direction of rotation of the plane of plane polarized light is opposite. So this would be dextro, this would be levo. Now dextro and levo only represent the direction of rotation of the plane of plane polarized light. It has got nothing to do with arrangement of groups in space or the configuration. Now I've held a paper, I've kept the model against a paper. Now the paper is a two-dimensional surface, just like a board, right? Now when I place so this representation is a three-dimensional representation. It's called the perspective formula. So we can represent optical isomers by two ways. This is what is going to be introduced. So first let me focus on the perspective formula. Alright, now this is the perspective formula. In the perspective formula, you notice that the blue bond, black blue bond is towards you, towards the observer. It is jutting in front of the paper. Now this is what is represented by a wedge. Okay. Now the red one, the orange one is projected behind the paper. This is what is represented by a dash. The purple and the green are lying in the plane of the paper. So purple and green are in the same plane as the two-dimensional surface. Whereas the blue one is the wedge which is projected in front of the paper, and the orange is the dash which is projected behind the paper. So we call this representation as the wedge dash formula or perspective formula. So let's focus on determining the configuration or the arrangement of groups or the absolute configuration with respect to the perspective formula first. So here is the perspective formula. Alright, now as you notice 1 and 2. So let me rewrite these numbers 1, 2, 3 and 4. Okay, so the board is in the place of the paper, the two-dimensional surface. On the two-dimensional surface, when we place the three-dimensional representation of the model, right, these two bonds were in the plane of the paper. So 1 and 2 are represented by solid lines. They are in the plane of the paper, two-dimensional surface. Whereas 4 is projected towards you, in front of the paper, and this is what is represented by a wedge. And this 3 is behind the paper, projected behind the paper and represented by a dash. Simple example represented here. Okay. Now we have COO. This carbon atom is bonded to 4 different groups. This is your chiral carbon or asymmetric carbon. Hence this can exhibit optical isomerism, can produce non-superimposable mirror images, right? Now you notice that COOH and OH are represented by solid lines. Fine. The H is bonded to carbon by a wedge. What does that mean? H is projected in front of the board, in front of the paper or the two-dimensional surface. Whereas CH3 is behind the surface, represented by a dash. So this is referred to as a wedge dash formula or the perspective formula. So this is an example for this perspective formula or the wedge dash formula. Alright. Now there is a way to determine the configuration, but let me tell you one more thing. The other representation is more easy to determine the configuration because this projection representation called the Fischer projection converts the three-dimensional representation to a two-dimensional representation. So Fischer projection is a two-dimensional representation. So let me first discuss how the three-dimensional perspective formula can be converted to a two-dimensional Fischer projection representation. Alright? Now, you have these groups. I hope it's clear to you. 1 and 2 are in the plane of the paper. 3 is behind the plane and 4 is in front of the plane, the wedge. Alright. Now, you view the molecule from this direction. Which direction? From an angle between the two groups which are in front of your view. In front of your view, you have 1. It may be in plane of the paper, but in front of you, you have 1 and 4. Right? So, view the molecule from an angle between two groups which are in front of your vision. Alright. And then we are flattening this. We are flattening this to get a vertical bond and a horizontal bond. Alright, so when we flatten this, when we are viewing through this angle, and when we flatten this representation, 1 and 4, the two groups which were in front of our vision, they constitute the components of the horizontal bond. So 1 is on the left, so 1 will be on the left. This 4 will be on the right. So these are the two components of the horizontal bond, right? Now the remaining two, this 2 is in the plane of the paper, 3 is behind the plane of the paper. These two will constitute the components of the vertical bond. Alright, so 2 is above and 3 is below. Okay, so let me make the numbers more clear. This is 1, this is 4, this is 2 and this is 3. Now in a Fischer projection formula, there is no need to show the carbon atom. You can draw two intersecting lines. Okay. The horizontal line will comprise of these two components, the components which were in front of your vision, alright, and 2 and 3 will constitute the components of the vertical bond. This is how you represent the Fischer projection formula. Okay. Now, for this example, look at the way the representations have been done. Now, we are viewing the molecule from between these two groups which are in front of our vision. OH is a solid line in the plane of the paper. H is projected in front of the paper or the board, right? So we view from an angle between these two. So these two constitute the components of the horizontal bond. So we are flattening this. So OH comes to the left and H comes to the right of the horizontal bond. COOH and CH3 constitute the components of the vertical bond. We remove the carbon atom and this is the Fischer projection formula. Okay, so you've been introduced now to two different projections or representations of a three-dimensional enantiomer. Alright, so it's very important that you understand this because in exams, in competitive exams especially, you may be given questions with the Fischer projection formula. So I'm letting you understand the connection between the two first. Now we will start discussing the ways to determine the configuration and then we will apply those rules and solve questions. Alright. So we have the Kahn-Ingold Prolog system. So this gives us rules to assign the absolute configuration for an enantiomer or optical isomer. You have the R and S configurations. So one absolute configuration is R and the other is S. R stands for right, in Latin rectus, means right or clockwise. S is sinister or left in Latin, anti-clockwise. So what is meant by what is this clockwise and anti-clockwise? We will soon discuss. But before we discuss that, we have you know that the chiral carbon is bonded to 4 different groups, right? So we have to assign priority to the groups attached around the chiral carbon. So there are some priority rules. Okay, so let's first discuss the priority rules and then we will discuss what is R and what is S configuration. Alright, okay. So priority order of groups or atoms around chiral carbon assigned. That is the first step to be done. Let's do an example. Let me write a representation here. This is our chiral carbon. Now these are the two solid lines. Okay, this is the wedge and this is the dash. It's a rough representation. Okay, now let me place groups around the carbon atom. Let this be hydrogen. I'm not placing any groups. I'm placing few atoms and some groups. What do I mean by groups? Let this be OH, that is a group of atoms. Let this be chlorine, Cl. Now another group of atoms, CH3. Alright, so this is a representation perspective formula of this particular compound. Okay, now focus on the atoms which are directly bonded to the chiral carbon. Okay, so this is the chiral carbon. This is the chiral carbon. Alright, so let's focus on the atoms directly bonded to the chiral carbon. So which are the atoms directly bonded to the chiral carbon? Oxygen, chlorine, carbon and hydrogen. Correct? Now we have to assign an order of priority. Okay? that is based on atomic numbers. Alright, that is based on atomic numbers. Alright, so we know that hydrogen has an atomic number 1. Carbon has an atomic number 6. Chlorine has an atomic number 17. Oxygen has an atomic number 8. So we know the atomic numbers. The one with the least atomic number is hydrogen. That has got the least priority. The one with the highest atomic number is chlorine. That has got the highest priority. So let me arrange the atoms directly bonded to the asymmetric carbon in the increasing order of atomic numbers, or hence the increasing order of priority. Alright, so we have hydrogen, least priority, less than carbon, less than oxygen, less than chlorine. Okay, less than chlorine. Let me just erase that part. Doesn't look very clear. Okay. So I'll just rewrite that part. So less than oxygen, less than chlorine. Alright. So that is the order of priority. Increasing order of priority. Increasing order of priority based on increase in atomic numbers. So now what do we do with this? Alright. So I'll try to explain it to you very briefly here, and we will discuss that in more detail a little later. But I want you to understand why are we arranging them in this particular order. Okay. Now, we have to, this is your molecule, right? We know the group of least priority is here and the group of highest priority is right here. Now, we have to view this molecule in such a way that from our vision, the group of least priority is away from us, is farthest from us. How do we represent a group on a perspective formula which is away from us? Obviously by the dash. So hydrogen has been placed, the group of least priority has been placed on the dash. What does that mean? Behind the paper, away from us. So that is the first rule according to this particular system of assignment of configuration. After we assign the priority order, we have to view the molecule in such a way that the group with the least priority is behind the paper, behind the two-dimensional surface, is on the dash. Okay? So in this particular, so all your questions will not have the group of least priority behind or on the dotted line. So I'll tell you how to convert that to the dotted line. We can do that as a next step. So right now, the most basic information is what I'm conveying, the simplest of the situations, right? The group of least priority has been conveniently placed on the dotted line. That means it is away from us. Ignore that. Now, you have to move your eye from you must start from the group of highest priority to the least priority, excluding the one which is already kept away on the dotted line. So focus on only chlorine, carbon and oxygen. Alright. So we have to move our eye from the group of the highest priority to the second higher priority to the third higher priority. Okay. And if our eye movement takes up this clockwise path. See, this is a clockwise path. Highest, second higher and the third one. Right. So our eye movement has taken the clockwise path, right? And therefore this has been assigned what configuration? Clockwise is right, or R configuration. So that is how we assign absolute configurations. We'll do a lot more examples a little later. Okay, fine. So I have given you the first way to assign priority. This was easy because you had different atoms attached to the chiral carbon. This is not always the situation. Okay, so let me take you to another example where you have two identical atoms bonded to the chiral carbon. So what do we do in these situations? Okay. Let me take a few examples. Now suppose, I'll draw a very simple picture here. Okay, let me just, I'm not drawing the perspective formula. Let me just write down the formula of the compound, the structure of the compound. Okay, so let's have, say, CH3. I hope it's clear. CH3, let me make it more clear. Okay. Yeah. So we have CH3, CH, okay, Br, CH2, CH3. I have not drawn a perspective formula. I have just drawn a simple structure. Okay. So first identify that there is a chiral carbon. Now this is the chiral carbon bonded to 4 different groups. One of them is a methyl, the other is an ethyl, then you have bromine and hydrogen. Okay. So here I am only teaching you not the assignment of configuration, I am only teaching you the assignment of priority order. Configuration, we'll do more examples. By the previous example, I'm sure you have a kind of an idea as to how to identify the configurations, right? Now, let's assign the priority. For that, focus on the atoms directly bonded to the chiral carbon. Okay, so which are the atoms? One is hydrogen, one is bromine. Now we have a problem. Alright, now if I were to write, what does CH3 imply? Let me make that more clear. Doesn't CH3 imply that? CH3 implies that it is like this, right? This is CH3, correct? What does that mean? On this chiral carbon is bonded to this carbon. In ethyl group, the chiral carbon is also bonded to this carbon. So you have 2 identical atoms, right? They're a part of different groups, but the atoms are identical which are bonded to the chiral carbon. So how will you compare their priorities? Okay, but before that, it's very clear that bromine has the highest atomic number, followed by carbon, and hydrogen has got the least atomic number. So there's no doubt about bromine and hydrogen. We have to now tackle between these 2 groups which has a higher priority, right? First step. Both these carbon atoms are identical. Now we look at the next point of difference. The next point of difference is this. In the methyl group, this methyl carbon is bonded to a hydrogen, whereas 3 hydrogens, correct? This ethyl carbon is bonded to, I'll write it here more clearly. This is your ethyl CH2 and CH3. This is ethyl group, right? Now look at this. The ethyl carbon is bonded to 2 hydrogens just like this. Bonded to 2 hydrogens just like the methyl group. Which is but the next point of difference comes now. The methyl group is bonded to another hydrogen, whereas the ethyl carbon is bonded to another carbon. This is the point of difference between the methyl and the ethyl group. Looking at the point of difference, hydrogen, this is the point of difference, hydrogen and carbon. Now assign the priority. Doesn't this carbon have a higher atomic number than this hydrogen? Therefore, this carbon will have, so the ethyl group will have a higher priority than the methyl group. This is how you compare the priorities when you have 2 identical atoms belonging to different groups around the chiral carbon. I hope it's clear to you. Okay, we'll do some more examples. So now let's assign the priority order of the groups around the chiral carbon. The one with the least priority is hydrogen, correct? So hydrogen is least, followed by methyl, followed by ethyl, followed by Br. Okay, so we have to view the molecule in such a way that the group with the least priority is kept away from us. that is on the dotted line. That we will discuss later. Okay, let's do one more example of assignment of priority and then we will tackle a few questions. Okay. Alright, suppose you have the structure, say let me take chiral carbon is here, let me fix one as say chlorine, let this be an OH. Okay, so here we have say CH2CH3 ethyl group, and here we have CH double bond CH2. This is the chiral carbon. This is your chiral carbon, asymmetric carbon. These are the 4 groups around the asymmetric carbon which are different. First, let's highlight the atoms directly bonded to the chiral carbon. So you have oxygen, you have a chlorine, you have a carbon here, and you have a carbon here, right? The group with the highest priority is the one with the highest atomic number. So here there is no doubt. Chlorine has the highest atomic number, so chlorine will have the highest priority, followed by oxygen. Oxygen has a higher atomic number than carbon. So second higher priority group will be oxygen, right? Then we have to compare between these 2 groups as to which will have a higher priority, correct? So chlorine is assigned priority number 1. This group, OH group, is assigned priority number 2. Okay? Now to compare the priorities of these 2 groups, let me write them down separately. Alright, so we have the ethyl group, CH2, CH3. Okay, and then this group, CH double bond CH2. Alright, now according to Kahn-Ingold-Prelog system, whenever there is a multiple bond, okay, what we've got to understand is this carbon is bonded to this carbon of the CH2 group twice, 2 times. If you have a single bond, this carbon is bonded to this carbon by only once. If you have a double bond, this carbon is bonded to this carbon 2 times. If you have a triple bond, this carbon is bonded to that carbon 3 times. What do we mean by that? Same thing can be written as CH. Now this double bond, I am writing it like this. One bond once, one attachment to CH2, another attachment to CH2. Double attachment to CH2. This is how when you have a double bond, this is the way you have to understand how the arrangement is done. Okay. Now let's look at the first point of difference between ethyl and the vinyl group. Okay. Let's assign priority. Now, this is the carbon atom. This carbon atom is bonded to 1 hydrogen. This carbon atom, I'll look at the structure for representation. This carbon is also bonded to 1 hydrogen. In the ethyl group, the carbon is bonded to another hydrogen, okay, and 1 carbon. This carbon has already been bonded to 1 hydrogen like this, but the second attachment is not to a hydrogen. Second attachment is to a carbon. Third attachment is also to a carbon. Here, the second attachment is to a hydrogen. Third attachment is to a carbon. Here, second and third attachments are both towards carbon. As a result of which, this group is assigned a higher priority than the ethyl group. So, we assign priority number 3 to this and priority number 4 to this. Okay, so I've touched upon certain examples that you need to be aware of. You can think about many other examples, but these are a few representative examples which will help you to tackle these kind of questions. Please watch the next video where we will apply whatever we learnt in this session and assign configurations based on the CIP system.